Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and as many of you know, I am one of the co-founders and I'm also a teacher here, along with my younger brother, AJ Raj. As you can see, we have a new Algebra 2 lesson today. It's going to be on polynomials, linear factors, and zeros. This is going to be part 1, and then the second half of the lesson is going to be covered in another video that comes after this in part 2. So we already covered everything about polynomial functions, as in the foundations, the basics that you're going to have to understand as we delve into this new unit. In this lesson in particular, we're going to be looking at how to factor a polynomial into linear as an x plus a number n factors that also are its zeros, and we'll talk about exactly what that is. So in this lesson, we'll be doing some very basic factoring in which we're going to be GCFing a polynomial, and then what remains is going to be something that resembles a quadratic that we can break down by guess and check method that we did in the last unit. And we're going to break these polynomials into linear factors. Remember, linear is pretty much x to the power 1. I'll write that here for you. So x to the power 1. Remember, when we say linear, we mean a line. And when we talk about linear equations, we have the y equals mx plus b equation that always comes to mind. In this case, x has an imaginary 1, exponent of 1. So that's how we derive linear. So remember when we talked about quadratics, we had x plus a number n is equal to times another x plus another number equals a quadratic. So for example, we had something like x plus 1 times x plus 1 gave us a quadratic that was equal to, and we multiplied it out by using a FOIL. So first, outside, inner, last, we got x squared plus 2x plus 1. These here will be considered linear factors because this is x to the power 1 and then x to the power 1. So we're going to be breaking these polynomials into their linear factors and then finding zeros using these linear factors. So before I even get into the lesson, I'd really appreciate it if you all could hit the like button, the subscribe button, and the post notification bell. Also drop a comment and share using all of our social media. And I wanted to quickly address this meme I had here. It says, with great power comes great difficulty in factorizing the polynomial. Like I said, in this lesson, we'll be doing some basic factoring where we're going to be GCFing. What's going to be left is a quadratic. We can easily use the guess and check method to break it down into 2 linear factors plus whatever we GCF'd out. But in the following lessons, we're going to be doing some more difficult factorizing, especially including cubes. So keep that in mind. I just thought that was a bit funny, so I wanted to include it. Okay, let's get into the first slide. This is going to be key ideas of the lesson that I want you to keep in mind. I always try to do this because I want you all to keep in mind why are we doing this lesson. So the first thing we're going to try to accomplish is we want to be able to analyze the factorized form of a polynomial. Like we said, we're trying to factorize these polynomials into linear factors. And when I say linear factors, recall from the previous slide, a linear factor is x to the power of 1, which is just going to be x, plus a number n. Linear factors are going to be x plus n times x plus n, as many as you need to multiply out so that you can get the polynomial. So we're going to try to analyze the factored form of a polynomial. We're also going to be trying to write a polynomial function from its zeros. Remember when we talked about quadratics, for example, I'm just going to write the quadratic I wrote from the last slide. We had x squared plus 2x plus 1. And when we factored this, we had x plus 1 times x plus 1. If you multiply these two out, you're going to get the x squared plus 2x plus 1. When we set these equal to 0, we were trying to find the zeros of the quadratic, meaning what does x have to be equal to so that this whole equation is equal to 0. In this case, we can see that the zeros are -1 and -1. And because it's a perfect square trinomial, so it only has 1 0. And if you remember when we graphed this, what did the zeros represent? Well, they represent where the graph hits the x-axis. So for example, this graph, it would hit the x-axis at it would hit the x-axis over here, and that would be the parabola. Similarly, when we graph these polynomials, we're trying to see where they hit the x-axis so we can determine their x-intercepts, which are also known as zeros, which are known as roots, which are known as solutions, etc. So we're trying to write these polynomials in, we're trying to factor them and find their linear factors, because remember, linear factors are equal to or equal to your 0. So in this case, the linear factor of this quadratic would be x plus 1. If I set x plus 1 equal to 0, I can find what the 0 is. If I subtract 1 from both sides, I get x is equal to -1, and that was a 0. So that's the same concept we're going to be applying in this lesson to polynomials. Let's look at the first problem. Let's just jump right in. Let's factor a polynomial. And you're probably wondering, Anita, why are we jumping in? You didn't even show us how to factor a polynomial. Well, this is where all the stuff we learned from the last unit with quadratics is going to play in, and I'll show you how. So the problem is, we're at the factored form of the polynomial, and we're given 9x cubed plus 6x squared minus 3x. So as you can see, this is a cubic. It's not in perfect polynomial form because we don't have a constant. We have a cubic term, we have a quadratic term, and we have a linear term. We don't have, I'm just going to call it c plus c. We don't have a constant term. So just keep that in mind, and I'll show you exactly how we're going to factor this polynomial using the methods we've already learned, especially the guess and check method. So here's the solution already pre-written for you if you want to just go ahead and copy that. I'm going to be running through that exact same problem with you, so no worries. First, I'm going to rewrite the polynomial we've been given, 9x cubed plus 6x squared minus 3x. First thing we want to do is we want to see, this is for any factoring you're doing. Can we GCF? Can we pull out something from this equation, a factor that all of these terms have in common? Because keep in mind, we have three terms here, 9x cubed, 6x squared, and negative 3x. Is there something I can pull out from each of these that's a common factor? Well, GCF stands for greatest common factor, and if you see, the greatest common factor here is 3x. I can pull out a 3x from each of these. I can pull out a 3x from the 9x cubed, and I'll be left with 3x. I can pull out a 3x from the 6. Sorry, I can pull out a 3x. I can pull out a 3x from this 9x cubed, and I will have a 3x squared. I can pull out a 3x from the 6x squared, and I'll have a plus 2x. And I can pull out 3x from this negative 3x, and I'll get a negative 1. So if I pull that out, I can rewrite this as 3x times, well, 9 divided by 3 is 3, x cubed divided by x is x squared, and I'm sorry, in the pre-written I wrote 3x instead of 3x squared. I apologize. Just make sure you correct that. Then I can pull out a 3 from the 6 by dividing it, 6 divided by 3, and I'll get 2. I do x squared divided by x, and I get x, and I do negative 3x divided by 3x. Well, that cancels out, and we're left with a negative 1. And if you see, what we're left with is actually a quadratic, and we can use the guess and check method that we've learned. The factors of negative 1 are going to be 1 and negative 1. So how are we going to pair these up? If you see, in front of the x squared, we have a 3. So because 3 also does not have any factors other than itself and 1, we're going to rewrite this as 3x times 3x plus or minus some number times x plus or minus some number. So we got to pick which parenthesis the 1 and the negative 1 are going to go in. Well, the negative 1 goes with the 3x, and the 1 goes with the x, and you would know this by doing a guess and check. So if we multiply this back out, 3x times x is 3x squared, 3x times 1 is 3x, minus x is the positive 2x, and then minus 1 times 1 is just equal to negative 1. So this here would be our final answer. This is the factorized form of the polynomial. We broke it down into linear factors. Okay, let's look at the next concept, roots, zeros, and x-intercepts. So here's the key concept that I want you to take away. The following are equivalent statements about a real number b. So b is a real number. B does not have any imaginary numbers, so b is not equal to I or any imaginary numbers associated with I. It's a real number. And here's the polynomial that we talked about before. P of x equals a subscript n times x to the power n plus a subscript n minus 1 times x to the power of n minus 1 plus ... Any other terms that follow after that in descending order, plus a subscript 1 times x plus a subscript 0. A subscript 0 is going to be your constant term. A subscript 1 times x is going to be your linear term. And then this first term here is going to be your greatest degree. For example, if we had a quartic, this would be a, whatever the leading coefficient is, times x to the power 4, plus what follows after. If it's quartic, then it'd be 4 minus 1. So this would, in perfect standard form, this would be a cubic. So it would be whatever the coefficient is times x cubed, plus that would follow would be a quadratic. then your linear, and then your constant. That's, remember, perfect standard form that we talked about before, with the leading coefficient having the highest degree and then every term coming after it having one less degree. Perfect descending order, perfect standard polynomial form where you have a term for every single power that comes after that leading term. And I just want you to keep that in mind. And along with this new concept we've introduced with a real number b, when I talk about these next four statements. So x minus b is a linear factor of the polynomial p of x. So remember, b is any real number, x, and let's just say, for example, b is 2. So the linear factor in this case would be x minus 2. So if you remember, when we broke quadratics down, we had like x plus or minus some number n times x plus or minus some number n. Well, in this case, you can think of b as that number n. So x minus b is a linear factor of the polynomial p of x. In this case, you can just assume that b is a positive number for this sake. It might be a negative number, but for this example, we're assuming it's a positive number. X minus b is a linear factor of the polynomial p of x. That means that x minus b times another linear factor times another linear factor times another linear factor, when all multiplied out, it'll give you this polynomial p of x. So look at the next statement. B is a zero of the polynomial function y equals p of x. Remember, zeros are where the actual graph of this polynomial crosses the x-axis. It's where the function itself, meaning y, is equal to 0. Therefore, b, if we plug in the value b, this linear factor, when we factor this polynomial and we get the linear factor x minus b, whatever b is, if we plug it in for x, we're going to get pretty much, if we plug b in for x, think of it logically like this. If we have x minus b as a linear factor, we plug in b because it's a 0 for x, you're essentially going to have x equaling b, and b minus b is equal to 0, and then all the other factors times this factor, which is 0, is going to make the whole polynomial function equal to 0. That's why b is a 0 of the polynomial function. It's a linear factor, but it's also a 0. B is also a root or a solution of the polynomial equation p of x is equal to 0. So remember, when p of x is equal to 0, it's essentially saying y is equal to 0, meaning you're literally sitting on top of the x-axis. And again, when we say root or solution, we're talking about zeros. We're talking about roots, solutions. Literally, you can think of it like the same thing. So in quadratics, because we had an x squared term, when we said root, we were talking about when we broke that x squared into x plus or minus some number times x plus or minus some number. So we were looking at essentially the roots of that quadratic. So in this case, you can think of it the same way with a polynomial. B is a root or a solution. And lastly, b is an x-intercept of the graph y equals p of x. Again, like I've been saying, b is going to be a 0. A 0 is essentially where p of x is equal to 0. But it's where x has some value that makes p of x equal to 0. When you plug b's value in for x, you end up having the whole function equal to 0, meaning x equals b, but y is equal to 0 at that value. And an x-intercept is where the function's graph is going to cross the x-axis. So all of these four statements literally mean the same exact thing. Your linear your b, in this case, the real number, is going to be a linear factor. It's going to be a 0. It's going to be a root. It's going to be a solution, and it's going to be an x-intercept of this polynomial p of x. So that's what I want you to take away. All right, so let's look at this next problem. Problem number 2. We're going to be talking about polynomial zeros. So here's the problem. Find the zeros and sketch a graph. We've been given a polynomial function y equals x times x minus 2 times x plus 1. As you can see, it's not written in our normal p of x. It's not written in p of x is equal to a subscript n times x to the power n plus a subscript n minus 1 times x to the power n minus 1, and then so on. It's not written in that form. So that way you can see it's not written in standard polynomial form. It's actually written factored for you. So it's already been factored for you. You don't have to multiply it out or anything. They want you to just find the zeros of this polynomial, and then using those zeros, make a sketch of a graph. See how it's a sketch of a graph. The graph doesn't need to be perfect or anything. We just have to sketch it using this, and just only plot the 3 zeros and then sketch it. So this is the solution already shown for you. I'm going to be going through this again with you. So we're going to be walking through it. Okay, so what we want to do first is we always want to rewrite the polynomial we've been given. So in this case, we've been given y equals x times x minus 2 times x plus 1. Keep in mind that when we're trying to find the zeros, like we did with quadratics, when we were told factor this quadratic, okay, then we factor it, and then they say find the zeros, we set the whole quadratic equal to 0, and then we looked at each linear factor. For example, this is one linear factor, x minus 2. This is another linear factor, x plus 1. And then x by itself is even a third linear factor. We looked at each one and we thought, how in this little set of parentheses or this set of parentheses can we set this equal to 0? So that we can find the value of x when this is equal to 0, because if x is equal to some value, for example, if x is equal to -1, in this parentheses, -1 plus 1 is equal to 0, and if we just multiply this times the two other linear factors, the whole polynomial is equal to 0. So that's what we did. So that's exactly what we want to do here as well. We want to set this whole thing equal to 0. So this is 0 equals x times x minus 2 times x plus 1. See how I literally just replaced the y with a 0, because that is the value of the function that we're trying to find. So when y is equal to 0 and the function is equal to 0, we're trying to find what x is equal to. So we can literally just look at each individual linear term. Well, if we look at each one, if x is just equal to 0, if we just make x equal to 0, 0 times whatever mumbo jumbo is in this parentheses times whatever is in this parentheses, 0 times both of these is just going to give you 0. 0 times anything is just 0. So in this case, x is equal to 0. Here, we would have to set x minus 2 equal to 0 and then solve for x by moving 2 to the other side by adding it. And you'll get x is equal to 2. And then we can do that with this. X plus 1 is equal to 0. So x is equal to -1. So our zeros in this case are going to be -1, 0, and 2. I just put them in order. So these are going to be our zeros. Now, how are we going to graph this? Well, we know that the zeros are -1, 0, and 2. So the first point we can graph is the point 0, -1. -1, 0. So I'm going to find that right here, -1, 0, and I'm just going to draw a dot over it to indicate that's where we're trying to plot. Next, I am going to draw a point at the origin, because our next 0 is at 0, so the point is going to be 0, 0, because y is equal to 0, x is also equal to 0. Our third 0 and our last 0 is 2, so the point is going to be 0, 2, y is equal to 0, 2, 0. I keep saying these backward, but 2, 0, x is equal to 2, y is equal to, sorry about that menu, y is equal to 0. So these are going to be our 3 points, but how does this graph look? Well, we know it's a cubic, so it's going to look something like this, but how exactly are we going to draw that? Or does it look like this? So we know that's the general shape, but we don't know which way we want to draw it. Well, we're going to apply properties that we learned about the leading term. I'll write that up here, leading term. Remember, the leading term was ax to the power of n. So we need to figure out what a and n are so that we can determine what is the end behavior of this graph, so we can properly sketch a graph. So the leading term in this case, we just need to look at the x's. If we FOIL this, we have x times x times x. So we know it's going to be a cubic. So I'm going to write that out. X times x times x is going to give us x cubed. Each of these x's have no coefficient, so this is going to be our leading term. X cubed is just going to be our leading term. We don't need to multiply the rest of the polynomial out. We just need to know the leading term. In this case, our coefficient is just going to be 1, and 1 is positive. Because imagine there's an imaginary 1. It's not -1, just a positive 1, because there's no negative sign in front of it. Our n, which is our exponent, is 3 because we're working with a cubic, and that is odd. So if you remember our little table that we looked at before, with the relationship between the leading term's coefficient and its exponent, this would mean down and up n behavior. Down and up. So your graph is going to look a bit like this, because we read this like a book. So your graph is going to go down on the left side, and it's going to come up like that, and then it's going to go up on the right side. So that's a very, very basic sketch of what your graph should look like with just using the 3 zeros that we knew of. Okay, moving on. So we're going to look at something called the factor theorem. This one's pretty straightforward. I'll give you a quick example. Here's the key concept I want you to take away from the factor theorem. The expression x minus a is a factor of a polynomial if and only if the value a is a zero of the related polynomial function. Okay, so let's do a basic example of this using a familiar quadratic. So let's say we have the quadratic x squared plus 4x plus 4. If we factor this, we can see that is a perfect square trinomial, so we have x plus 2 times x plus 2. That is pretty straightforward. If you multiply this out, you should get this quadratic. So what we're trying to say here is the expression x minus 0 is a factor of the polynomial if and only if the value a is a 0 of the related polynomial function. Well, if we set both of these equal to 0, when we look at the second one, the factored form, we're pretty much saying x plus 2 is equal to 0, and then x has to be equal to -2, right? And that's the same for this one because remember, perfect square trinomials have only one 0. So the same thing applies for this factor. Well, if this is the 0 we get, we have to plug it back into the original polynomial, and this right side has to be equal to 0 if we want to claim that x plus 2 is a linear factor of this quadratic. Well, let's plug -2 back in. -2 squared is equal to 4. 4 times -2 is -8. 4 minus 8 is equal to, actually, I'll write this out for you. So if we plug in -2 squared plus 4 times -2, we're just plugging -2 in for x, plus 4 to test to make sure it's a 0. -2 squared is 4. 4 times -2 is -8, plus 4. 4 minus 8 is equal to -4 plus 4, and then you're just going to get 0. So yes, this is a linear factor. The reason we say this is because we can't just claim that a random linear factor, like for example x minus 1, is an actual linear factor of this quadratic, because the 0 of this linear factor is -1, and if we plug -1 into this quadratic, it doesn't give us 0. So that's what this factor theorem is trying to say. It's trying to say that this expression x minus a, this linear factor, is a factor of the polynomial only if it works as a 0 for the polynomial. So trying to establish the relationship between factors and zeros. Okay, everyone, I'm back with a new view. This one's going to be of my calculator because this next problem is going to involve the calculator after we just do the work for the problem. I'll show you exactly what I mean now. So here's problem number 3. We're going to be comparing zeros of a polynomial. So we're going to be looking at two different polynomials. One's going to be a cubic, one's going to be a quartic. Then we are going to figure out what the zeros are. Then we're going to go on the calculator and plot them on the TI calculator just to save us some time, because if we have this resource, we don't need to do it by hand. So then we're going to look at them on the TI calculator and then compare their graphs. Okay, so let's get right into it. So the instructions are: write the standard forms of the following polynomials and graph on the TI to compare both of them. So here's our first polynomial. All we've been told is that the zeros are -2, 2, and 3. So you might be wondering, how are we going to determine what the standard form is? Because if you remember, standard form is px of a times x to the power n plus a times x to the power n minus 1, and so on. So that is standard form. So how are we going to get it in that standard form just from the zeros? If you remember, the zeros also double as linear factors. So we can rewrite these as linear factors. I'll show you how. So here's the work. We're going to rewrite these as linear factors. So to have a 0 of -2, you're going to have a linear factor of x plus 2. Because if you set it equal to 0, x plus 2 equal to 0, if you subtract 2 from both sides, you get x equals -2, which is the 0, -2. So we're going to rewrite each of these as zeros. So we're going to have x plus 2 for a 0 of -2, x minus 2 for a 0 of 2, and x minus 3 for a 0 of 3. So you're pretty much, you can think of it this way, you're swapping the sign and putting it after an x. That's how we represent all three of these zeros. So you get y equals x plus 2 times x minus 2 times x minus 3. If you multiply x minus 2 times x minus 3, you get x squared minus 3x minus 2x plus 6. We have to multiply that times x plus 2. But before we do that, we can simplify the linear term. So we can do -3x minus 2x is equal to -5. So we do x plus 2 times x squared minus 5x plus 6. Multiply all of that out. We get x cubed minus 5x squared plus 6x plus 2x squared minus 10x plus 12. So we can combine like terms. We can bring the x cubed down. We have the -5x squared. We add the 2x squared to we get -3x squared. And then we have a 6x minus 10x, which is -4x. And then we just bring that constant term plus 12 down. And that is going to be our polynomial standard form. This is going to be the cubic. Let's look at the next one. Here's a quartic. So the zeros are -2, -2, 2, and 3. And you might be confused because you see -2 occur twice. Well, we're going to be talking about something called multiplicity on the next slide. That's where a zero can occur more than once in a graph. But we're going to treat them as though they're two separate zeros when we write this when we write the linear factors. So we're going to have y equals x plus 2 for the first negative zero of -2. We're going to have x plus 2 for the second zero of -2. We're going to have x minus 2 for the 0 of 2, and then x minus 3 for the 0 of 3. If we multiply these out, we get x plus 2 times x plus 2, and then if we multiply x minus 2 times x minus 3 out, we're going to get x squared minus 3x minus 2x plus 6. If we simplify that by doing -3x minus 2x, we get -5x. We can multiply that times x plus 2, the first x plus 2, and we can get x plus 2 times x cubed minus 5x squared plus 6x plus 2x squared minus 10x plus 12. We can simplify all of that to x cubed minus 3x squared minus 4x plus 12, which is actually the polynomial we worked with in the last problem. And all we have to do to finish this off is multiply it times x plus 2, and we get this long multiplied out equation, x to the fourth minus 3x cubed minus 4x squared plus 12x plus 2x cubed minus 6x squared minus x plus 12. If we combine like terms, we can bring the x to the fourth down. We do -3x cubed plus 2x cubed, which is -x cubed. Then we do -4x squared minus 6x squared, which is -10x squared. We can do 12x minus 8x, which is 4x. And then we have plus 4. Yes, plus 4. Okay, sorry, I see one mistake I made. At the end of the second to last line, it should be plus 24, not plus 12. So your final equation should be y equals x to the fourth minus x cubed minus 10x squared plus 4x plus 24. That's my bad. So just keep that in mind. Make sure you make that correction if you're copying this down. Okay, let's get right back to the graphing calculator. We're going to go to our y equals just because we want to plot this. So in our y1, we're going to plug in x. We're going to plug in the first polynomial we had, which is x cubed minus 3x squared. Minus 3x squared minus 4x plus 12. And then in our second one, we're going to plug in the second polynomial, the quartic. We had x to the fourth minus x cubed minus 10x squared plus 4x plus 24. Make sure you make that correction, plus 24. Now I'm just going to hit graph. We're going to see them graphed here. So this here is going to be our cubic. You can see the zeros are at -2, 2, and 3, and then the quartic comes after. You see this bounce almost here at -2, and then you see zeros at 2 and 3. Keep in mind this bounce right here of the red graph as we go to the next slide when I explain multiplicity to you. Okay, that's the first calculator. Do this one next. Okay. Okay, 3, 2, 1. Okay, let's move on to another calculator problem. In this one, problem number 4, we're going to be investigating multiplicities. So we're given the problem, find the zeros, state all multiplicities, and describe end behavior. Okay, so let's get right into it. The polynomial we've been given is f of x equals x to the fourth minus 2x cubed minus 8x squared. So first, we're going to have to find the zeros. Well, how are we going to do that? We are going to first factor it. As you can see, we can GCF an x squared from each of the 3 terms, so we can rewrite this as 0 equals, because we're trying to find the zeros of this polynomial. 0 equals, if we factor that x squared out, we get x squared times, well, x to the fourth divided by x squared is x squared, minus 2x cubed divided by x squared is just minus 2x, and then 8x squared divided by x squared is 8, so we get minus 8. Now you can see we're left with a quadratic, and if you look at the quadratic, we can actually break it down into 2 linear factors by a guess and check factoring method. So we get x minus 4 times x plus 2. If you multiply that back out, you get x squared minus 2x minus 8. So then we get x squared times x minus 4 times x plus 2. So our 3 linear factors. Well, if you look at the x squared equals 0, we can just square root both of the sides, and we get x is equal to 0. So that's one of our zeros. Then we get x minus 4, and we set that equal to 0. Add 4 to both sides, x equals 4 is another 0. Then we set x plus 2 equal to 0, and we get x equals -2 as another 0. Well, how are we going to identify the zeros? Well, we have a 0 of 4, like we said. We have a 0 of -2, as we said. But if you look at the 0 of 0 with the x squared, you're going to see that when you square root it, you get x equals 0. However, when you square root a number, you technically have two solutions. You have the principal root, which is positive, and then your negative root. So, for example, when we square root 9, we have two answers. We have 3 and we have -3. So in this case, the graph actually hits 0 at 2 times. So it's going to bounce at 0, like we said in the last slide. So it's going to have a multiplicity of 2, which you would indicate by saying mult dot, just abbreviate it, and then 2. Or if there's a multiplicity of 3, you would write 3, whatever you need. And as you can see from the leading term, which is x to the fourth, if you go back to the top of the screen with the original polynomial, a is technically 1, which is even, and then n is technically 4, which is an even number. Sorry, a is technically 1, which is positive, and then n is 4, which is even. So the n behavior is going to be up and up. So if I sketch this polynomial, this quartic, just by using a graph, just by using like a sketch, that's what it should look like. So let's graph it here on the calculator. Let's just plug in the original x to the fourth minus 2x cubed minus 8x squared. Actually, no, let's plug in what we found with the zeros. Let's plug in, just to check that we're right, x squared times x minus 4 times x plus 2. You don't need to simplify to standard form. You can just do it like that because it's going to multiply out all of those linear factors for you, and we get the correct answer. So that's how we solve that problem. Okay, so that was a very interesting calculator problem. So let's get into a topic called multiplicity that you saw in that last problem that you might not have understood. So let's address that. So what does multiplicity mean? Well, it's a term that describes zeros that occur more than once. So if you think of multiplicity, it's almost like multiple. So multiple means numerous or more than one. So this term pretty much describes when you have zeros that occur more than one time. In all the examples we've seen so far, like for example, with quadratics, we usually had a quadratic that we could factor by the guess and check method, and we broke it usually down into two linear factors. And then those two linear factors were things like x plus 2 times x minus 3, or x plus 9 times x minus 6. And then based off of those, we would find the zeros, and then we would usually have two different zeros where the parabola intercepted the x-axis. Well, when we kind of go past those baby steps, we look at polynomials that go up to degrees of 3, 4, 5, etc., you're going to have instances where the polynomial actually hits a zero 2 times. So that's what this term means. It means that zeros that occur more than once. So for example, in the last problem, we had one of the zeros was -2. However, the polynomial crossed that zero 2 times. And you might be confused as to how a graph could cross 1, 0, 2 times. Well, that's what multiplicity has to do with. So we would literally say from that last example, the graph has a zero of -2 with a multiplicity of 2 because it hits that point 2 times. So let's look at the effects of multiplicity on graphs. Multiplicities of zeros have the following effects on graphs. So here's a little table I made to help you better understand this. So if a zero has multiplicity 2, 3, 4, so I just gave you scenarios. This is what it's going to look like on the graph. So if a zero has multiplicity 2, that means the graph has that zero 2 times. So it crosses that zero twice, like in the last example. If the graph has a multiplicity of 3, then it hits that zero 3 times. If it has multiplicity of 4, it hits that zero 4 times. So the graph will appear quadratic at that 0. So it's going to be even and it's going to bounce. So what does that exactly mean? So quadratic. So you can think of it like this almost. X squared, x cubed, x to the fourth. Because as you see, I wrote here quadratic, cubic, quartic. And that's what these exponents pretty much stand for, right? And this is what's denoting the multiplicity. It hits it twice, it hits it 3 times, it hits it 4 times. So it's going to look quadratic at that 0. So if you had a 0, for example, at, 1, and you had a multiplicity of 2 at 1, it's going to appear quadratic. And what do quadratics look like? Well, they are a parabola. They bounce. That's why I wrote bounce. So it's pretty much going to bounce at that 0. Whenever you see a graph bounce at a 0, that indicates a multiplicity of more than one, especially when you're working with polynomials. That's why I wrote bounce. Even in my notes, I wrote bounce to help me better understand how a multiplicity of more than one can occur. So if you see a little bounce like we did in the last problem, that can indicate that there's a multiplicity at that 0. If a multiplicity of 3 occurs, it's cubic at that 0. If a multiplicity of 4 occurs, it's quartic at that 0. So cubic functions look like this. Sorry about the bad drawing. Quartic functions actually look like a parabola, but they're a bit flattened. They look like that. So if you see a graphical behavior similar to that at a 0, then it can indicate that there's a multiplicity of 3 or 4. So that's what this chart is pretty much trying to tell you. And also look at how I wrote even. So even multiplicities are kind of similar. For example, they kind of bounce or flatten. That's why I wrote bounce here. They bounce or flatten at a 0, so that could also help you graphically if you look at stuff visually and you're trying to understand multiplicities. So that's all on multiplicities. Not too complicated. Just keep in mind that it is possible for a polynomial to cross 1 0 multiple times, and you'd indicate that like we wrote up at the top, x equals -2, and it has a multiplicity of 2. Okay, this is another calculator problem. So you can insert the second calculator part here. And I'll do the conclusion slide. Okay, everyone, that's the end of the video. I hope you enjoyed. This was on polynomials, linear factors, and zeros. We looked at the relationships between factoring and then looking at linear factors and how they play into also being zeros of polynomials when we graph. I hope you enjoyed. If you did, please like, subscribe, and hit the post notification bell. Share using our social media. Check out our website and email us using our Gmail, eCoreAcademy@gmail.com for anything at all. Thank you for watching, and stay tuned for the next Algebra 2 video.